In this problem, we're returning to spaceships, so I am very excited. Now, similar to what we saw in Units 1 and 2, we want our spaceship in this case, or it's actually a satellite, to get into orbit. However, this is a very special type of orbit. It's a geostationary orbit. What this means is that once the satellite is in space at a certain distance away from the Earth, it will orbit the Earth at exactly the same rate as that at which the Earth rotates. So to people on Earth, it's going to look like this satellite isn't moving at all, which is pretty cool. To show you how this happens, we have this lovely diagram right here, which I warn you is not to scale. In the center, we have the Earth, and initially the satellite is orbiting at just 200 kilometers away from the Earth's surface. Now at a certain moment, in fact at the moment when the rocket first crosses the x-axis on this diagram, the rocket is going to spit the satellite out. And this is going to propel the satellite away from its original orbit and eventually out to the radius that it needs to be at for geostationary orbit, so this red line right here. Then it's going to stay along this red path for as long as it needs to. Now the radius of geostationary orbit is 42,164 kilometers. Also, just an interesting tidbit, this transition orbit, this green curve right here, is exactly half of an ellipse that's tangent to both of these circular orbits, the pink one and the red one. Also, these orbits are both perfectly circular, even though my drawing doesn't really show that. So there are 3 tasks that we would like you to complete for this problem. The first of these is to find out what the speed and radius of that initial smaller orbit is. Remember, like I said, this is a circular orbit, so that should make things a little bit simpler. You'll probably have to use pencil and paper for this part of the problem. Now, when the rocket and the satellite attached to it cross the negative part of the x-axis for the first time, the rocket fires its engine to increase the speed of the satellite by the amount given in the variable called boost. This should remind you a lot of the last problem of Unit 2. So for your second task, we want you to figure out how to make this boost happen, and of course, how to make it happen at the appropriate time. Let's go back up a bit in the code to look at your last task. This is going to be to figure out, as you've done before, what the correct magnitude of the boost velocity is. We filled in a dummy value of 42 just to start out with, and we've given you several different options to choose from. One of these is the correct answer. Once you've completed the first 2 tasks, plug in each of these values for boost and compare the plots to see which one helps the satellite enter geostationary orbit.